excited to be here. It's my first time, so I already got a little bit of a tour just on the walk. But thank you everybody for joining and for attending. My name is Jeff Maroney. I guess there was a bio already, but just as a quick introduction, I think I have a slide on it. This is me. So I went to school in Colorado, Boulder. So I graduated from there with my PhD in power electronics, and then from there I joined. Let's see. Oops. Oh wow, look at that. I joined National Semiconductor, and I worked out of Colorado and National Semiconductor's research lab. It's called NS Labs at the time. And after that, about 2 years later, we were acquired by Texas Instruments. And so, of course, I joined TI at that time. And I've been doing corporate R&D my entire professional career, essentially. So I've been working in the research lab there, starting in Colorado still, and then moving to Dallas about 8 or 9 years ago. You can see I got a family up here. So 3 boys, 8, 6, and 2. And so when I'm not at work, they definitely keep me busy. So that's just a little bit about me, but I'm really grateful to be here, really excited to talk to you today about the semiconductor industry, about how TI approaches semiconductors and how we do research in semiconductors. And then one particular trend in semiconductors that if you're watching the news, you may be familiar with, and that's the trend of AI, artificial intelligence, and what's that kind of look like, and what's the implications of it in our world. So really looking forward to today, and thanks again for having me. Okay, so I kind of mentioned this, but I think this is relatively early. It's only been about 2 weeks since class started, so I wanted to give a 101 on semiconductors. I'm not sure how many of you are familiar with it. You talk to my wife, and I tell her what a semiconductor is or a chip is, and she thinks it's food. So I want to at least give you guys some grounding on what is a semiconductor, how is it made, and what's the process that goes into it. I do want to talk a little bit also about the way that we do R&D in TI and how we structure that, and try to explain a little bit less about the specific technical investments, but more about the strategy of how we do R&D, because I think it's a unique model. I think it's a very exciting model, and something that we're pretty proud of and that we've really spent a lot of time perfecting. And then last but not least, artificial intelligence and power associated with it. So I didn't mention this in my bio, but my power electronic, or my PhD at Colorado was in power electronics. So right now is a pretty exciting time to be in that world, specifically related to power associated with these NVIDIA processors and these AI processor ecosystem. Okay, so what is an integrated circuit? This is a little bit debated, I would say, but I think it's mostly a consensus that the integrated circuit was invented by Jack Kilby on September 12th, 1958. Jack Kilby was at Texas Instruments when he invented the integrated circuit. So the lab that I'm a part of, you may have already heard, is Kilby Labs, named after Jack Kilby. And what this basically was a collection, a very small collection of transistors on a piece of, on a substrate. In this case, it was silicon germanium. You can see kind of a picture of it there in the bottom left. So that's where it really all started. And he won the Nobel Prize for this. And what's happened since is semiconductors have exploded everywhere. And I want to give you a little bit of a sense why and some of the reasons that have gone into this. But in case you don't know what a chip is, besides food, it is this. And you can see I picked this picture because there's a Texas Instruments logo, so I had to give a little bit of credit. But these are inside of everything we have. And what does that mean? Every electronic that you interface with has some form of semiconductors in it, whether it's the computers or the laptops or the tablets that you have there, whether it's in automotive electronics. It could be any vehicle systems. It could be your motor control. It could be your seat heaters. It could be your windshield wiper motors. It could be your self-driving parking assist. All of those are fundamentally enabled by semiconductors. Industrial. Industrial is a little bit more of a broad one, but think robotics, industrial robotics, where you have these robots or arms that are moving things around. This is all driven by semiconductors. Enterprise is what we call data center. So if you're not familiar with the term, this is, you go Google something and you get a response. This is how. And it's all, again, fundamentally enabled by semiconductors. So although most people don't necessarily appreciate it, when you go buy something, you buy the end product. You buy a computer or a phone or whatever it is. That all is really fundamentally a semiconductor solution. And so that's what we do at Texas Instruments. That's the foundation of that was established by Jack Kilby's invention in the previous slide. Okay, so what's happening in the semiconductor market? Why is it such an exciting place to be? This is a picture that actually TI publishes on our investor reports. And it kind of is intended to show what's happening in the world of semiconductors as a trend from the late 80s all the way through today. And what's on the y-axis is what's TTM is trailing 12 months. So basically, this is the number of semiconductor units that are shipped into the world on a trailing 12 months average. And you can sort of see what has been happening. We start in 1989 in the 10 billion units or so monthly average. And in today's world, we're in a little bit of a downturn right now, but in today's world right here, we're in the ballpark of 90 to 100 billion units. So really an exponential growth in semiconductors that are being consumed by the world, consumed by this room, consumed by all those industries I showed in the past. You'll also notice there's sort of an interesting cycle here that we go through. So you may or may not recall that during some of the COVID stuff, there was a semiconductor crisis. The semiconductor crisis was basically that there wasn't enough capacity in the world to support the demand for semiconductors. And that happened exactly during this time here to here, during this slope up here. There was a lot of semiconductor demand, and all of the fabrication facilities, all of the things around the world that build these didn't have capacity to keep up. And so there's been a lot of work, that's partially why there's a CHIPS Act. There's been a lot of work going into making sure that we can sustain this trend because it's appearing to not have an end in sight. So this is kind of at a high level what is going on in the semiconductor industry and why I think it's very exciting. But there is a question, I guess there's a typo here, but there is a question, why is this? Why are semiconductors proliferating? Why is that happening? So I have a little bit of an animation here, but I'll start by saying that I may not be right about this, but I can't think of any other industry in the history that is anti-inflationary. You go buy a Coke 10 years ago and you buy it today, it's more expensive today than it was 10 years ago. The only industry that I'm aware of, or that I can at least think of, that is anti-inflationary is semiconductors. And that's why that chart on the previous slide exists. Every year we build semiconductors and we work to make them cheaper. And what that enables is more and more semiconductor adoption, more and more proliferation. And so how does that happen? Well, if you just look at historically, the factories that we build have been subject to inflation. The factories that we use to produce semiconductors are about 1,000x more expensive compared to 30 years ago. But we have 10x higher yield, 100x larger wafers. So these chips are built on wafers. I'll show a picture on the next slide. But these wafers are getting larger, so we can fit more chips on those wafers. And we've gotten really good at pushing throughput out in our factories. So a really key part of the cost equation here is how many wafers can you get out per hour. So we've done a lot of work within the industry to drive that. So you kind of combine all that and you get a fixed cost silicon real estate. So now you kind of look at it and say, okay, everything is fixed cost there, but we go now to Moore's law. And Gordon Moore was a famous Intel person who defined a law that said these chips are going to get smaller every generation. And now we start to see, okay, 2002 to 2015, how much smaller these chips have gotten. So now this is why we've been able to defy the laws of inflation. Our chips are smaller, they're getting cheaper and cheaper. We're able to fit more and more of them into a certain area, and eventually you defy inflation. And there's lots of ways of looking at this. On the power side, we look at it in this figure of merit, and it kind of shows a similar trend. But I think just to put this in perspective in terms of the scaling laws that I'm talking about here, I think it's useful to use an analogy. So this Moore's law that I mentioned that drives a law that our chips get smaller and smaller significantly every generation. If batteries followed Moore's law and you imagine what the batteries looked like 30 or so years ago, you could drive an electric car 300 miles with a battery that costs $1 that fit into the palm of your hand. That's just, I think, an amazing analogy of how powerful what we've been able to do in the semiconductor industry is in terms of making these things affordable, smaller, and cheaper, and enabling more and more electronics in our lives year on year. Okay, so how is a semiconductor built? Just for the sake of time, I won't go through all of this in too much detail, but I want to just give a high level because I think it's also a good, especially as you're kind of earlier in your college studies, I think it's a good summary of the opportunities that exist and the diversity of opportunities. So, semiconductor manufacturing process at a high level, you start with a bare wafer. These are silicon wafers, that's why it's called Silicon Valley. And so these wafers come in different diameters. 300 millimeter is the most common diameter these days, so it's about 12 inches diameter. And we do a whole bunch of steps. These steps include deposition, photoresist, lithography. These are all used to essentially pattern wafers to build semiconductors, to build transistors on these things. So that goes through multiple steps, and you can kind of see the circular loops there. And that eventually results in a processed wafer. So now this wafer has got a whole bunch of small chips on it that do these functions, but it's in a wafer format. So in order for us to take it from wafer format into something that looks like the chips in the black kind of packages that I showed you before, we have to do more work. So in that case, then we dice them so that you can kind of see they get singulated, and we attach them to a substrate. We bond them out. Wire bonding is how you electrically connect to and from the wafer. And we encapsulate, which means we put it in a package where it has a plastic mold compound that goes around it. And now we test it. And this is obviously at a very high level, but this is kind of the semiconductor processing at 30,000 feet. What opportunities exist here? Process engineering. You have to come up with ways to develop these process nodes and to be able to engineer them. Quality control. We're building literally billions and billions of units a month. You kind of saw that on the other slide. How do you ensure that they all work? So you have to have very good quality control, very good test engineering. We test all of our wafers and all of our devices that come out to make sure that they work. Semiconductor physics, device physics. Packaging technologies, that's kind of more of a mechanical engineering background, but being able to package these and model the stresses and model the ability of these things to survive in those packages. Industrial engineering and AI is kind of an interesting one too, and it's more emerging, I would say, but how do you use AI and these machine learning algorithms to optimize your factories so that you can churn out more parts, you can get smart about the process steps and the efficiencies within the factories. And then analog and digital circuit design. So eventually you have a process that has a whole bunch of components, and you need a circuit designer who can put those all together in a way that gives you a chip, gives you something that serves a function. So that's the kind of process and the opportunity on that side of things. You also have what happens afterwards. So this is when it starts to get real. This is when the systems start to get developed. So now you have a chip. You can put that chip into a system. That system could be in this case, this is a picture of a battery charger for an electric vehicle. And you can sort of see all the stuff that goes around it. There's all these passive components. These fins here are heat sinks to cool the part. This is a transformer. This is an EMI filter. You take these chips and you put all these components around it, and you enable something in an end system that's useful. And that ends up going to customers. So in this case, then, there's lots of opportunities in engineering systems, applications, marketing, sales, of course, finance, operations. So we kind of touch all of it within the semiconductor space. And as I said, I don't know if there's a more exciting place to be right now, just due to the growth of semiconductors and the ability of us to scale cost and to do new things every year. Okay, so that's on the semiconductor side. Let's talk a little bit about, just make sure I'm doing okay, I know we're late, on R&D investments and how we approach R&D within TI. So Kilby Labs is our advanced R&D. It's a corporate R&D organization within TI. And what we do is the advanced research for TI. So we work on the most disruptive, most challenging, difficult problems within TI. We collaborate with customers to understand the problems. One of the most difficult things, most important things I should say, is what is the problem you're trying to solve? And we partner with customers. In fact, part of the reason I was late is because I was visiting one of our bigger customers in California and flew here this morning. So we work very closely with customers to co-develop capabilities, to co-define problems, and to eventually see high-risk, high-reward R&D to fruition all the way in the form of revenue and end products. We're based across these sites here. Dallas is our headquarters, Santa Clara. Freising is just outside of Munich and Tokyo. And this is kind of just, in a nutshell, the ingredients that it takes. The first thing is a customer problem. You have to have a real problem that you're trying to solve. If you have that with a disruptive technology, something that nobody else has that really solves a real problem in a unique way, you are off to a great start. Collaborative development I'm going to talk a little bit more about because it takes a lot of different people and a lot of different skill sets and a lot of different ideas and backgrounds to solve problems. Passion is maybe one of the more important ones because this is hard. And there's oftentimes you'll develop something, you'll be in the middle of it, and it'll take an unexpected turn. And you really have to have the passion and the persistence to accept those challenges and to pivot and to eventually get to the end solution. And the initial idea isn't just the fun part. Part of the fun part is how do you navigate the real world of what you discover as you're developing that idea into something that actually can be produced and solves a real problem. So how do we do that in TI? What we basically do is we rely on people, hopefully, that'll eventually be coming out of rooms like this. So we hire what we call them as NCGs, new college grads. And these are people who have new ideas, new energy, fresh perspectives. And we partner them with very experienced people within TI. And we form joint teams. These joint teams are staffed across Kilby Labs and the businesses. And we together co-develop these ideas. And you sort of get a professor-student relationship in some way where you get somebody who's willing to challenge assumptions. Why are you doing it this way? Why not try it a different way? And sort of think outside the box with somebody who's been doing it for 20 or 30 years who has some lessons that they've learned over those years. And you get that together with a group of people who have a single goal, and you can really get some special outcomes. And that's the fundamental model that we've started with. Beyond that, we think about this as fail fast. These are high-risk ideas. These are challenges that nobody's ever really encountered. And so I don't want to fail after 4 years. If we're going to fail, we should fail after our first few months. So what that means is that you have to identify the newest, most risky parts of those ideas and think about how to test those first. And if you do that well, you'll learn what works and what doesn't work without spending somebody's 4 or 5 years of somebody's hard work and dedication on an idea that may not pan out. So that's why we have sort of a phased approach here where we increase our investment as we learn more and more because we get more and more confidence. And eventually what we do is we build a demonstration. And that demonstration says these are the high-risk parts of this idea, and here it is in real life working. When that demonstration works from a product group perspective, from the people that we work with in the businesses, they shouldn't be able to distinguish from a risk perspective this idea versus any other idea that they would go develop that might be considered lower risk. We've essentially de-risked the idea. So at that point in time, what we do is we take the researchers within Kilby and we transfer them into the businesses. And so what we avoid is we don't have a baton passing, if you want to use an Olympics analogy. There's no baton passing. The same team, the same core team that was working on this idea in the high risk phase takes it all the way through to fruition. And that's really important too, and it's also, I think it's fun to see because the people that were in Kilby, they don't want to leave their project. They've developed a passion for it and an enthusiasm around it. So they want to go with their projects all the way through to the eventual release and then mass production of it. This is their idea, this is their baby, it's something that they've really invested in. And so this concept has worked really well, and I would say that if I contrast it to what we used to do 10 years ago, what we used to do 10 years ago is we would develop an idea in Kilby and then we would throw it over the fence to the businesses that are responsible for productizing it, and then we'd get mad when they didn't do it. And you have to realize at that point that there's a psychology, there's also a joint ownership that goes into it. You want people that co-develop these ideas together, and if there's no joint ownership of the people that are going to be responsible for the productization of it, we call it not invented here. There's a not invented here syndrome where it says, well, I don't know why you made this decision, or why did you do it this way, or why didn't you think about this? If they're not part of it from the beginning, the odds of success are lower. So that's how we've modeled our R&D, and I think it's really been successful. The other thing that we did is that we decided that we're going to hold ourselves accountable to the same metrics that you would imagine others in businesses do. Our metric is revenue, and the time scale for revenue may not be the same time scale as a shorter term, lower risk effort, but it's still revenue. And we actually track revenue for the developments that came out of Kilby. And I think in the last 5 years, it's close to $2 billion. And so thank you, I'm excited about that too. But I think that we've learned a lot about the model, and in the end, our goal is to solve problems for customers, and we can measure that by the amount of money that they're willing to spend on the parts that we build and sell. Okay, so this is what it looks like inside of Kilby. It's a very collaborative environment. One of the best things I like to see is walking in and seeing two people like that in the left corner, whiteboarding, knowing that those two people are working on different projects. Because the other thing that we have in Kilby is a whole bunch of different skill sets and disciplines. Those job functions I had on that other slide, they all in some form or another exist within Kilby. And so now you get people from different backgrounds with different experiences, and then they think about problems from a different perspective. And you get an idea that you may not have gotten if you just had all the same people thinking all the same way. Okay, so just for the sake of time, I'm going to skip this and just go to the last section. AI and power. So how many people have heard of NVIDIA? Let's see. All right, good. All right, well, that's who I just came from. So I know them well, and obviously they're at the heart of this AI boom right now. And I want to explain a little bit about what's going on there. So this is really from a power perspective, not from the actual end function. But from a power perspective, I think it's really an amazing time. So within these AI processors, historically, you can kind of see it plotted here. The power required to use these things has gone up significantly generationally. And you can see CPU power, so that would be your normal Intel or AMD type of CPUs. You'd find them in your laptops or in any other form factor like that. They've gone up at a certain pace. These accelerator cards, or these accelerator processors, are going up at a much more dramatic pace. And you start looking at it and you say, okay, in 2025, we're expecting to have about 1,000 watts of power consumed by one of these processors. This was published at this OCP forum in 2023. I think it was in October of 2023. So let's say about a year ago. This is what people are actually talking about today at customers. So the actual numbers, this chart, in other words, was grossly wrong. People are talking about 3,000 watts, 3,000 amps per processor. And so the amount of power that these things are consuming is growing at a scale that's difficult to sustain. And I think I have on this a little bit of a history, or a little bit of a view of that. So NVIDIA ships, this is a public document, they ship to all these different people. And our friend Mark Zuckerberg here is building a AI server farm next to a nuclear power plant. And so you just start to get a scale for how much power is actually going to be consumed by these things. And it's not sustainable, but it's also a huge opportunity for somebody who does power management for a living. And so it's really an exciting time, an exciting area to be. And if you just look at this OpenAI, Microsoft AI data center, it is estimated to consume about the amount of energy that's consumed by 4.1 million US homes. And I come from Dallas-Fort Worth. I think the combination is the 4th biggest city in the country. We have 2.9 million homes in Dallas-Fort Worth. So you just get a scale for these little chips that I showed you, how much power they consume based off of this kind of story. So this is a little bit about how a buck converter works. I can't get through a talk without talking about how power electronics and power management. I won't go through it too much, but I want to just give you a little bit of the nutshell of what basically a power converter is that powers these processors. There's a voltage here. That voltage is modulated, so this switch turns on and off, this switch turns on and off the opposite way, and it gives you a voltage here that's filtered by this passive network, this L and C, and that goes to the output voltage. And you can have many of these put in parallel to power a huge processor. So sometimes you can, I'll show you in a picture on another slide, but many of these are used in parallel to provide all the current that's required for these processors. Now what TI builds, or at least what historically chips are, the semiconductors are these switches here. This thing here and this thing here. And kind of like I showed you on that other picture, everything else is external. You have inductors, you have other passives. Those are not part of the semiconductor, they're part of the system. But I'll explain how that's now starting to change because of that plot on the previous slide. Okay, so this is a traditional CPU. I don't know actually whose this is, it might be Intel's, but you can sort of see now this network here. So these chips here are those switches. You can see a few of them. These things here that sort of have the orange center, those are the inductors. And you can count them. There's 12 to 16 of them per processor, per CPU. So that's not that many. It's been that way for a while, but let's say 12 to 16 of these, you put them all in parallel, and that's how you can now produce power for hundreds of watts type of range. Now you look at NVIDIA's latest Blackwell card. And is there an animation? Yeah. So these things in red, and it's hard to see it, and I should have even zoomed in, but these things in red here, those are all power stages with inductors. There's 150 of them. And that's required to conduct maybe, let's say, 2,000 amps or so, 2,000 watts of power, 2,000 amps of current. So the opportunity is gigantic for people in power management, and it's getting to the point where the power solution is no longer a nice to have, where people just say, give me the power and I want it to turn on my processor. You have to develop better power solutions in order for these systems to work. Otherwise, you're going to need nuclear power plants sitting next to data centers. And so what are people doing about that? Now, this is just a little bit of an architectural view. So if you recall the previous slide, all of these things are sitting side by side with the processor. And so in a cartoon drawing, you can kind of see here, 12 volts in, 0.8 volts out. This is the processor, and this is that power converter with many of them stacked in parallel. And what I've got drawn here is the wire that connects the output of our power converter to the input of the processor. And if you guys know Ohm's law, 250 microohms of resistance, which is not very much resistance, and 1,000 amps of current would result in 250 watts of loss. That's today. Now I mentioned that in the future we're talking about 3,000 amps. So if I just do the same calculation, I get for 3,000 amps and the same resistance, resistance between the output of my power converter and this processor, I get 2,250 watts of loss, which is about the average power consumption of 2 homes. So the stupid wire that I have connecting the output of my power converter to the processor is burning more power than 2 homes. So that has to change. That's a huge fundamental limiting factor. And so what it means is that people are starting to do what's called vertical power delivery. So vertical power delivery is when you take this whole thing and you place it directly underneath the processor, and all of the current flows directly from the output of this into the bumps of the processor. So the path is much shorter and the resistance is much less. So now I do the same math, and now at 3,000 amps, I get back to 225 watts of loss. That's a little bit more manageable. But in order to do this, I now need to have something that took up all that space, all those red boxes that I showed you. It needs to now take up the space of a processor. It needs to be about that big. So call that 4 or 5x smaller. So we call that in our industry power density. You have to improve the power density by a huge factor for this to become real. So the way that, that this would actually look then, and what matters here, is what we call surface density. And I need now to be able to conduct all that across the surface area of the processor. And if I can do that, I can enable this much lower power loss. I'll skip some of this just because of the time constraints, but as I mentioned, the key requirement here is power density. And so this goes way beyond semiconductors. So what are people doing now? They're building what we call power modules. This is an example of a power module you can find online where it's got the semiconductor components. But now we're not only doing that, but we're integrating all of this other stuff into the semiconductor product. We're integrating the inductors, we're integrating the capacitors. We put it all together. And now a solution that used to look like this, where the semiconductor is a part of the solution, we're building the whole thing. And that whole thing can be a lot smaller, it can be a lot more efficient, and it can now enable vertical power delivery. And so what's, to me, really exciting about this is that the lines between a traditional semiconductor and a system solution are starting to blur. We are building system solutions. We're putting all this stuff together because that's what's required from our customers to solve these problems. Okay, so with that, semiconductors, what are they? Oops. What are they? and why they matter. I think you can hopefully appreciate that they're becoming an increasingly more important part of our lives, and it spans everything. It spans all the industries I mentioned, and I think even new ones. I didn't talk about it today, but a great new example is medical. We're building medical devices that can, for example, with microfluidics, can measure pathogens in your blood, and it's a semiconductor solution. And so there's just a whole frontier of things that you can imagine are going to get enabled by semiconductor technology because of the laws I mentioned and just because of the capabilities that are being enabled. TI, of course, we're the largest analog semiconductor company in the world, and we really believe that advanced R&D is not a nice thing to do to participate in the semiconductor industry. It is a prerequisite. And it's because of the reasons I'm talking about. Things are getting more and more difficult. Semiconductors are scaling more and more. The opportunities are kind of growing more and more wide. And we really have to advance the R&D and the innovation in order to enable all these things that people want to do. AI power. Power is no longer a necessity, but the key to unlocking future trends. I think that's particularly exciting because truthfully, when I graduated, it wasn't that power was the critical limiting factor. It is becoming that way, and it's not just in AI. It's in a lot of things. It's in solar power or grid power. It's in electric vehicles. Power management is becoming a critical part, not a afterthought to these solutions. And so I can't not plug that if you want to get into semiconductors, it's a great career choice. And if you want to get into power management for semiconductors, I also think that's a great career choice. But there's opportunities everywhere. There's opportunities, I think that's the last slide then. There's opportunities across many different areas in terms of functions, engineering, non-engineering, supply chain is mentioned here, software. There's lots, I think, of opportunities, and I think the opportunities are only going to grow and become a more important part. So, with that, I appreciate everybody's time and attention, and sorry I was late, but thank you for attending.
I'd really like to thank you, Jeff. You did a great job, like a running stop, directly to presentation. So one thing I might comment, to also put some of his work in context, the powers he was talking about for the NVIDIA chip are the same as for a spot welder for welding metal together.
Yes.
So he's having to build systems that are so precisely controlled, they power the AI chip rather than weld it to the circuit board. It's exactly the same energies. Yeah. Now, we have some minutes for questions and answers. I have a mic here, and I'll also repeat the question for the camera. If you guys have got anything you particularly want to bring to... Oh, yes. Let me just bring in the mic.
So I know that you do like advanced design for power management. Mm-hmm. Have you guys worked with superconductors? Like, I mean, that's the stuff that doesn't have resistance, I guess. Yeah. And I know it's not feasible in normal temperatures, but like, what are your thoughts on that?
Yeah, I mean, I think it's a good question. I think there was an article, wasn't there an article published like a year ago where somebody falsely claimed they could have a room temperature superconductor? So that would be very nice. But what I would say in just terms of R&D is, and the way I think about it is that not all R&D is created equal. There's short-term, mid-term, long-term R&D. So we are definitely engaged in those topics. But the way I think about it is that for topics that are more further out like that, we engage with universities. And so we actually have a couple projects, not on superconductors, but a couple projects with Purdue that are more further out device physics, more further out device design. And that really becomes an important part of the funnel of ideas and funnel of capabilities that will come into TI. And so we invest in all of it. The superconductor one, I think, fits into the category of university for us right now. But we do invest in it and monitor it and in some ways steer it.
Got it. Thank you so much.
Yeah, thanks.
Any other hands? Well, that makes my life easy.
I have a different kind of question, but how come...
It works, but it's for the...
Oh, okay. How come the wafers are circles?
So there are people talking about square wafers right now, but traditionally they've been circles because that's the way that... So it all comes back to the tool manufacturers. These tool manufacturers have historically built wafers in geometries that are circles. It's also convenient from a dicing perspective. But it is an important question because in the end, our, our wafers are circle, but our dies are square or rectangular. And so there's a perimeter around the wafers that we end up throwing away because you can't have like half a die. And so there are people looking at, not recycling, but square wafers, but there's a gigantic ecosystem that services everybody that's circle wafers. And so I doubt we're going to see in the short amount of time square wafers. But if you want to accept a mental challenge for yourself, think about a geometry that's better than a square. I have an answer to this, so it's not like you can say one of like, oh yeah, that's the right answer. But a geometry that's other than a square that would allow you to get more chips out of a wafer, a circular wafer. I don't think, yeah, maybe there is one. Maybe you can come up with one. But
Let me just hand some folks over here for a second.
yeah, sure.
So are you guys still able to keep up with Moore's law?
Yeah, so Moore's law is less applicable to our products now. So what Moore's law scaling did was, you'd go from like 65 nanometer to 45 nanometer to 28 nanometer, and now TSMC and Intel are trying to get to 2 or 3 nanometer. And so TI about 15 years ago decided we didn't want to run that race because it's very, very expensive. Basically, you need to retool factories every time you go to the next lithography. So there's another category, and this is often confused even in the media, there's another category of semiconductors. They call them trailing edge. I don't love that term because we do very advanced work, but trailing edge means it's on trailing edge nodes. So like 130 nanometer, for example. And that is just fine for products like power. So in order for us to keep up with the requirements, we don't necessarily need to follow Moore's law going down and down on lithography. What we need to do is things like system in packages and better ways of putting these devices together. And so when you think about analog semiconductors, they're less influenced by Moore's law compared to like a processor that you might used to thinking about.
You already answered a lot of my questions, but I kind of have a little bit of a longer question.
Sure.
So I was an intern in an iron mill, and our future state processes, they were very easy to map. Our main goal in mind was to get the cost of iron, to make iron per pound less than to make steel per pound.
Okay.
And so it was very easy to look at our future state and how we wanted to develop our factory. My question for what TI does is, with all of your research and development and customer needs and changing ecosystems, how exactly can you form a future state in mind for your factories, considering all those elements?
Yeah, so there's multiple different aspects of it to it. Let me talk to it from a factory perspective, but also from a customer perspective. So there's multiple metrics that you could think of in factories like ours. So a couple of relevant ones that are just known in the industry. One is we call cost per pattern. So when I talk about these alternating semiconductor steps that are used to build an IC, those steps are called patterns. And the more patterns I have, the longer it takes to process that wafer, the more expensive it is. And so if I can reduce the number of patterns, if I can reduce the number of masks, sometimes it's called, that reduces cost. But if I can also, for a certain cost per pattern, drive my cost per pattern down, then I can build those for cheaper. And so, for example, one important metric in our fabs is cost per pattern. How do I improve cost per pattern? I can drive more wafers in an hour, for example. And so there's things like that that we think about from a cost perspective that are, I think, very fundamental. If I think about assembly sites where we package these parts up, we think about what we call nubs. How many units can we ship out in an hour? And the more I can churn out, the lower cost I can get. So there's constant efforts to try to improve manufacturing efficiencies, to try to drive lower and lower costs, higher and higher throughput. On the customer side, the way I think about it is trends. So what I want to do is I want to think about areas where if I go talk to a customer 10 years from now, that area still matters to them. Power density is a good example in power management. 30 years ago, power density matters. 30 years from now, it will matter. And so if I make fundamental investments in power density, the products may not work out. The products may be misdefined, or may they have a problem, they may be late. but the capability of enabling power density will serve us well. And so when I think about that, we call them power trends, but when I think about it, that's what I think about. How can I do something that makes power density higher? And if I can do that, I will enable something. And if I can continue to do that over years, I will have a future state that, that will serve us well.
Well, I love your questions, and I'm sure Jeff
I do
does
too. I'll stay here all day if I
Officially,
could.
this is the end of the lecture, so if you guys have questions, want to come to the front and ask them. Otherwise, can we give Jeff a round of applause?
Thank you very much. Thank you for the questions. Thank you.